Okay, so so far we've been playing around with right triangles only. And with right triangles, which is a very powerful tool and is the foundation of all right triangle trigonometry, is Pythagorean theorem and SOHCAHTOA. And it seems like this is just a matter of you guys scraping some rust off and possibly extending some of these to the third dimension and so on and so forth. But what happens when we no longer are dealing with right triangles? For the next couple of questions, you might need to know something about non-right triangles. And so, what about if we're dealing with all possible right triangles or all possible triangles in general? In other words, are there formulas that govern equilateral triangles, scaling triangles, isosceles triangles, and right triangles? One formula that rules them all? Well, pretty close. It's technically two formulas that rule them all, and we call them the rule of sine or sine rule. In America, we generally call it law of sines. Since IB is not stationed in America necessarily, they call it sine rule. Look for either one online. You should find both pretty helpful. And then the other one is called the cosine rule or law of cosines. So let's go over this. Notice that my nomenclature is the exact same everywhere you look. Across from A is side A, across from B is side B, and across from angle C is side C. Same thing here. Across from C is side C, across from angle A is side A, and across from angle B is side B. So this nomenclature is always the same. Given this information, we can find or we can utilize the law of sines. And law of sines simply states that the ratio of sine A over the side A has to be the same ratio as sine B over the side B. Has to be the same ratio of sine angle C over the length of side C. So all these ratios have to be true no matter what triangle you're dealing with. So we can start solving for various sides here and there, and they don't have to necessarily be a uh, right triangle. Now, I generally use this particular version of it when I'm looking to find an angle. The reason being is because the angles are already in the numerator. I don't have to solve too hard to get the angle by itself in the numerator. Down here, obviously, if they're asking me about trying to find a side, I'm looking to, oops, hello, to find a side, then I just take the reciprocal of everything. And again, I'm putting the sides on top. It just makes it easier. Honestly, it doesn't really matter if you always pick this particular version or always pick this particular version. If you plug everything in where they belong and you know your algebra, you're fine either way. So pick one and go with it. All right. Oh, by the way, the sine rule generally works with if you're given angle, side, or angle sides, or I should say side angle. And you'll see why that works in just a minute. I'll do a few examples with you, but keep an open mind when you're looking at a triangle. They're not going to tell you to use law of sine or law of cosine or rule sine rule cosine rule. You're just going to have to recognize that you have these two options. So definitely use the sine rule. Okay. All right. In a similar instance, we have the cosine rule. And we use that whenever we have side or side. So we're kind of covering all of our bases. We can give pretty much any kind of triangle, give you any setup, side, angle side, whatever it is, and there's going to be some way of getting to your solution. Now, the law of cosine or cosine rule is a little bit more sexy. The good news is this should look sort of familiar. It looks like Pythagorean theorem, right? This is sort of just an adjustment to the Pythagorean theorem. And here is our adjustment. Now notice all you need are the three sides or an angle. All right. If I gave you all three sides, then this would be the only missing piece. You could solve for it. That's why side works. Or I can give you two sides and the angle in between. Notice whatever goes over here, this is its opposite angle over there. Opposite side, opposite angle. That's the only thing that really matters. I could relabel where I put A, B, C. I could rearrange it so I could have several versions of this equation, this formula. But so long as this angle over here, or sorry, this angle over here and this side over here are opposites, and these are your other two, right? Then it doesn't really matter. You're going to be fine. And we're going through a few examples of that. Okay. Now, that's one version of cosine rule. I typically use this when I'm looking to find a side. Now, I generally only memorize this one version, and this is it. I usually only memorize this version and I'm done. From year to year as a math teacher, if I got that down, I got no problem. However, some students find it difficult to solve for the angle. And in order to get cosine theta or cosine A by itself, if I solve for A, this is another one that sometimes students like to memorize because this is the one I would use if I'm looking to find an angle. Because then I can just plug all my sides in over here, right? And I can just take the inverse cosine and I'm done. So there you go. It's a nice little setup. All right. So these are your four, well, technically only two. Like I said, this one and this one are your two general equations. Everything else is just an addendum of that. All right. So let's see how to play with this. Let's take example one here. Call that example one. And we have, well, we have side angle side, right? They gave us a side, an angle in between, and another side. So, oh, hang on a second. So we're going to use the cosine. And remember, so long as this angle is always opposite this side, then we're set. You can use law of cosines. So I'm going to say x squared is equal to 12 squared plus 17 squared minus 2 times 12 times 17 times the cosine of 47. And that's how you set it up. All right. Remember, so long as this goes on this end and its opposite angle goes on this end, everything else goes in between. All right. And let's see. This is pretty ugly. So I think I'm just going to say x squared is equal to, and whip out my calculator. 12 squared plus 17 squared minus 2 times 12 times 17 times the cosine of my degrees. Yeah, I am. 47. And boom. Oh, and don't forget, I'm going to have to take the square root of that in the end. So let me just go ahead and do that now. Square root of that answer. So I have 154.745, 154.745 approximately, and x will be approximately 12.44, 12.44. And that is in centimeters, and we just found our missing piece. All right, but that's it. It's just substitute and evaluate. You just got to be able to use those formula. All right. So let's see. Move on to example. We'll call it example number 2. In this case, I have 3 sides. I have side, side, side. So I want to still use the law of cosines. All right. And the law of cosines looks like this. One more time. Let's go a squared is equal to b squared plus c squared. It's 2 times b times c times the cosine of big A. All right. So I want to know what this is. So I'm going to call that theta. I'll say cosine of theta. The 15 goes over here. So I'm going to say 15 squared is equal to. And now the other two, the B and the C, it kind of doesn't matter what order I put it in, right? I could say 17 squared plus 10 squared and 17 and 10. Notice these two are interchangeable because it's multiplication. And these two are interchangeable because it's addition. So they're both commutative. So it doesn't really matter what order you put those two guys in. And the rest is just solving. Or you could use that other formula that already has everything solved for you, right? But let's take a look. If I just move these two terms over, 15 squared minus 17 squared minus 10 squared is equal to negative, oops, 2 times 17 times 10 cosine of theta. All right, let me work this out real quick. Let's go 15 squared minus 17 squared minus 10 squared. Boom. It's negative 164. Negative 164 is equal to, and you know what? Let me work this part out real quick. What's going to be negative 2 times 17 times 10. Whoops. Hello. All right. And we get negative 340. Negative 340 times the cosine of theta. Of course, I can divide by negative 340. And I'm going to get the cosine of theta is equal to, what is 164 divided by 340? Whoops, hello. And I get 0.48235. 0.48235. But I got to take the inverse cosine, which should give you the right answer. So inverse cosine of that answer, 61.16 degrees. 61.16 degrees. And I just found my angle theta. Done. Okay. Once again, it's just getting used to knowing that those formulas exist, getting used to substituting those values in there, and then just solving for any missing piece. Okay. All right. So that was laws of cosine. Down here, let's see. We do not have side angle side or side side side. We have angle angle side, right? Angle angle side. So that's a case for law of sines, or the sine rule, which simply says that these two make a ratio, right? The sine of 50 over 20 must be equal to the sine of 60 over x. Now notice I could have done this either way. I could have set it up like this. 20 over the sine of 50 is equal to x over the sine of 60. Which one's easier to solve for, right? I didn't take my own advice. I should have used this, put the x on top first, but it doesn't really matter. I mean, if I just do a quick cross product, I'm going to get x times the sine of 50 is equal to 20 times the sine of 60. Over here, I'm going to get 20 times the sine of 60 is equal to x times the sine of 50. And I can simply divide both sides by the sine of 50. And there it is. X is going to be equal to whatever the heck this is. And same thing down here, right? So I am just going to type in 20, move this up a little bit, 20 times the sine of 60, oops, divided by the sine of 50. And I get 22.61. 22.61. And that's it. And since this is in centimeters, I get 22.61 centimeters. Done and done. All right. So that's just using the law of sines, just using this little setup, right? And so long as it's always this angle over its opposite side is equal to this sine of this angle over this opposite side, you're only going to have one variable and you're good to go. Let's try that one more time. But this time we're going to say is before. This time we're looking for an angle. But again, this time they gave us an angle and then a side and then a side. Oops. Side angle. That's what I wanted to say. Okay. But still, once you recognize that you're using the sine rule, right? Then it's just a matter of saying, let's do a different color here. The sine of 60 over 20, sine of 60 over 20 is equal to the sine of theta over 10. Sine of theta over 10. Now, to get theta by itself, I could just multiply the 10 over here. Okay. I could reduce this. That's going to be sine of 60 divided by 2. Sine of 60 divided by 2. Once you really get to know the unit circle, you're going to say, oh, the sine of 60, I know that one. It's root 3 over 2. So you'll be able to jump from here to root 3 over 4 and just in your head. But that's the unit circle talking. We don't know the unit circle just yet. So I'm simply going to take the inverse sine of both sides. If I do, I'll get theta left on the other side. I'll get inverse sine of the sine of 60 over 2. And I can just let my calculator do the work and say second inverse sine times, second inverse sine, and I can say maybe 0.5 times. So I'm already put my half in there right away, times the sine of 60. And boom. And there you go. So theta is approximately 25.66, I'll say. 5.66. Did I get that right? Yeah. And that's going to be degrees. And there you go. And of course, once you know one angle, once you know two angles, you could easily find the third angle because they all add up to 180, right? So you found all three angles. Okay. I'll let you guys figure that part out. All right. So just to wrap things up, you are going to be able to utilize um, two primary equations. That's these guys right here. Law of sines and law of cosines. Hopefully you've actually seen this before, and this is just a refresher. But you're going to need those two to help solve any type of triangle you want. And it works for right triangles or equilateral triangles or whatever you want. Okay, good luck.